So we finished relative dating, and now we're going to look at radiometric or absolute dating. And the big difference here is this method allows us to determine the age of something in years. Okay, it's very different. It involves something called radioactivity and half-lives and isotopes. Okay, so let's take a look at this bird here. Well, is it a bird? This is the famous Archaeopteryx, which has a few weird characteristics for a bird. You can see its feathers are imprinted in this volcanic ash. This was a bird that got overtaken by a volcanic eruption in Germany a long time ago, and the ash, basically it succumbed to the ash and was buried at the bottom of a pond or a lake. And this was done so quickly that its feathers were well preserved. But this is a really old fossil, near the time of dinosaurs. It is the time of dinosaurs. It's a transitional time where the reptiles were becoming bird-like, and you can see it has feathers, and it even has feathers at its tail. But what it has in its tail, it's different, is its bones. It has this long, bony tail. Birds don't have that today. They just have long feathers that stick out of their rump here. Okay, and there are some other things that are not as well developed. It doesn't have as large of the pectoral bone, the chest bone, so it doesn't have. There's no evidence here that this reptile was actually able to fly the way we see birds flying today. It was more of a glider, and also you'll notice it has claws, so it hadn't given up its fingers and fingernails yet. And if you could see its skull, it's not really a beak. It's a head, it's a skull, and it has teeth. Birds don't actually have teeth. They have serrations in their beak, but that's not the same thing. Bird beaks are more like your fingernails. So there's differences here. But another problem with this is that this thing is so old that you can't tell what it is, or you can't do carbon dating on it. We can't figure out its age based on any material that's left over here because the animal's been petrified. So we use some isotopes and half-life concept to determine how old this is by looking at the age of the rocks around it. The fossil's not going to tell us, but the rocks we can get an age of. So let's see how we do that. Okay, there's the basics of radiometric dating is that all rocks contain radioactive isotopes, and they decay. They literally just kind of fall apart from big atoms to smaller atoms. You can see that we're starting over here with the biggest atom with a mass of 238. This is an atomic mass. Okay, and when this process, it looks like a little ping pong ball machine here as it goes down from one to the next, but finally you end up with lead. So what it means is that radioactivity means an isotope is unstable. Well, uranium 238 is unstable and it wants to fall apart, and it does that by shooting a helium nucleus out of its nucleus. All right, and we won't worry too much about the specifics of that. All right, and then it becomes thorium as a result, 234, and then it shoots off an electron, and then it goes through a process where it does a nuclear change between neutrons and protons, and it becomes palladium. And again, this just keeps going. Look, it's back to uranium, but it's a lower mass uranium. It's not 238, it's 234. Eventually, it gets all the way through all of this, going back and forth. Some of these get reused. Here's lead, and here's lead again. But notice the mass just keeps getting smaller until finally it gets to an isotope that's not radioactive. All right. Well, the thing that we care about is this thing called a half-life. How long does it take for half of these uranium isotope atoms to decay and become lead? Just half of them. How long on average does it take, a statistical average, to go from this to this, for half of it to turn from this to this? All right, and uranium 238 has a half-life of 4.5 billion years. That means if you had 100 uranium 238s, it would take 4.5 billion years for 50 of them to become lead, for half of them to become lead. Okay, so that's the concept. So here you can visualize it another way. Imagine that you have a glass of water and you're going to take a drink out of it every 2 minutes. So you start out with a full glass of water, and then after 2 minutes, you fill the glass. 2 minutes later, you drink half of it. So your first gulp, half is gone. Then, if you wait 2 more minutes and drink half of that, now half of this is left. And then, if you take another gulp, you're going to drink half of that. Okay. So when you get down to here, when you've drunk half of it in 2 minutes, and then waited 2 minutes and drank half of that, and then waited 2 minutes and then drank half of that, by the time you get to here, how much time has passed? That's 2 minutes, 2 more minutes, and then 2 more minutes. So it's taking you 6 minutes to drink that much water. How many half lives had gone by? One half life, two half lives, and then three half lives. What if you drank another gulp 2 minutes later? Instead of 6 minutes, now it's 8 minutes. And now you have how much of your original left? You had half, 1/4, 1/8. Now you're at 1/16. Okay, you see what's going on here? It's always half of whatever remains after each half-life. The half-life concept applies to whatever's remaining. So how long would it take to finish this glass of water if you're always drinking half of whatever's left? And let's assume water doesn't evaporate. It would take you infinite amount of time. Okay, so let's see what that looks like as a graph. So here was your full glass of water, and then you drink half of it after 2 minutes, and then you drink half of that, and half of that, and half of that, and you can see where this is going. Okay, but this isn't a glass of water. This is carbon 14, and carbon 14 has a half-life of 5,730 years. Okay, I'm just throwing it out there so you understand that. Here it is, right here, 5,730. So if you started out with all of it, 1 out of 1, if you had all the original carbon 14 in, let's say, an old woolly mammoth, dead woolly mammoth, and then after one half-life, you have half of that carbon 14 left. So it'd be 5,730 years old. But what if you found it and it had only 1/4 of its original carbon 14? So you had all of it, then you had half of it, and when you take half of a half, you get a quarter. So now you've got two half-lives that passed. One, two. How old is it now? 11,460 years. And there are many woolly mammoths of that age, because that was near the end of the Ice Age. Okay? And if we go three half-lives, from all of it to half of it to 1/4 of it to 1/8 of the original carbon 14, it's now a 17,190-year-old woolly mammoth. Okay, and you can see that this process can continue, and you can go back to about 30,000 years, possibly with new technologies 50,000 years. But once you get down here, what's the problem? Is you're running out of carbon 14, and it's getting harder and harder to measure it accurately enough that your errors are not bigger than what you're measuring. Okay, so carbon 14 is good for things that are relatively young. And what else? They have to be made of carbon. And what things are made of carbon? Living things, things that were once alive. So you wouldn't date rocks with this, because rocks are not living. Minerals never lived. Carbon 14 is for things like fossils, fossils that still have carbon in them and are not older than about 40 or 50,000 years. All right. So what method would you use for this frozen woolly mammoth? Well, I kind of gave it away. It would, since it was once a living thing, it's got carbon in it, it's not that old. This is all original tissue here. That's fur on its face and skin. You know, if you found this in the frozen north, you could cut it up and feed it to your dogs. Here's a baby one down here. You would use carbon 14 on its way to becoming carbon 12. And Lucy here I'm not going to talk about. And TRex, what would you do with this? Now, TRex, this is an interesting problem. Yeah, that's a dinosaur fossil. It's got bones, but those bones are no longer made of bone. They've been petrified. So if they've been petrified, that means the minerals, silica, have replaced the bone, which means there's no carbon there. And even if you could find some carbon bone in there, what would be the problem? Dinosaurs lived too long ago. So you can't use carbon 14 because dinosaurs lived millions of years ago. And carbon-14 is can only go back around 50,000 years. So what are you going to do? Well, you're again going to have to age date the rocks around the dinosaur. And sometimes you can't do better than finding a rock layer that tells you it's younger than this but older than this. So a lot of our ages on dinosaurs are going to have the word about in the front because we don't really know exactly, plus or minus tens of millions of years. Okay, so is that our last slide? It is. All right, so that's the concept of radiometric dating, and you're going to go to the lesson on that. And in your document, there'll be another video that leads you to a short explanation of how to use the lesson. Okay, and you must watch that or you'll have a difficult time with it. Okay, thank you.